Hello, today we're going to learn about the inverse transform, Laplace transform, and then how to handle transforms of derivatives, and then apply all of that to solving a differential equation. So first we start with the inverse transforms. If big F of s represents the Laplace transform of a function little f of t, then the inverse Laplace transform is little f of t equals Laplace inverse of big F of s. And so we're using that -1 exponent form to represent inverse function, not a 1 over function. Okay, it's not a reciprocal thing. It's just to give us that name inverse. To find little f of t, we're going to have to use the table of inverse transforms, which that's also in your book, and it can be read from any Laplace transform table, just reading it backwards, okay? But here we've got some inverse transforms written out explicitly, all right? So the goal is that whatever we're taking the inverse Laplace transform of, it has to be in the right form so that we can find it on the table. And if it's not in the right form, then we might have to do some major algebra to get it in the form, maybe some minor algebra. We'll see. So if we take the Laplace inverse transform of 1 over s, that gives us 1. The Laplace inverse of n factorial over s to the n plus 1 gives us t to the n. The Laplace inverse transform of 1 over s minus a gives us e to the at, and the Laplace inverse transform of k over s squared plus k squared is going to give us sine of kt. And the Laplace inverse transform of s over s squared plus k squared gives us cosine of kt. So these were the 5 that we saw in the previous section where we were taking the Laplace of the left-hand side to get back f of s. Now we're going to be taking the Laplace inverse transform of big F of s to get back little f of t. So let's see how we can do this with a few examples. In this first example, we're trying to find the Laplace inverse of 4 over s. So I look at what I've got here, and I'm looking at the first Laplace inverse transform. It looks like I could use the table to find the Laplace inverse of 1 over s, but I have 4 over s. So I'm going to pull the 4 out in front and say I'm actually finding 4 times the Laplace inverse of 1 over s, where again I'm just using linearity to help myself out. And then Laplace inverse of 1 over s is just 1, so my answer is 4. Okay? Now let's look at something a little more complicated. Laplace inverse transform of 1 over s squared plus 17. I'm looking at this one. And the reason why I chose sine of kt is because I would be taking the Laplace inverse of k is a number, over s squared plus k squared. Notice with the cosine of kt, you would have to take the Laplace inverse of an s over an s squared plus k squared. The thing I'm dealing with here is a 1, not an s. It's just a number. I cannot just simply introduce an s in a numerator. That would completely change the problem I'm working with. But I can get really tricky with my algebra and introduce a number, okay? So I'm looking at this denominator, and the 17 tells me that k squared is 17, so k is the square root of 17. That means I need a square root of 17 in my numerator. So this is equal to the Laplace inverse of square root of 17 over s squared plus 17. But no, it's not. I can't just arbitrarily multiply a square root of 17 in. However, I can, on the outside, multiply by 1 over the square root of 17. And then I've balanced things out because technically what I've done is just multiply everything by a root 17 over root 17, which is a funny looking 1. So now that it's in the form that I need, I know that k is square root of 17, so this all becomes 1 over the square root of 17 sine of the square root of 17t. And that's it. So that was the minor algebra that can happen. Let's look at this next one. Laplace inverse of 4 over s to the 5th power. okay? I want to rewrite this. This is the Laplace inverse of 4 over s to the 4 plus 1. Oops. And then I'm going to go upstairs and look really quick. So I'm looking at b, t to the n. So Laplace inverse of n factorial over s to the n plus 1. Okay, if I look down here, n is 4. Okay, so what I need is a 4 factorial in the numerator. I don't have a 4 factorial in the numerator, but what I do have is a 4, and maybe I could introduce multiplying by a 3 times a 2 times a 1. Let's see. So this is equal to the Laplace inverse of 4 times 3 times 2 times 1 over s to the 4 plus 1. But I can't just, again, arbitrarily put a 3 times 2 times 1 in a numerator. I have to also divide by that, 3 times 2 times 1, which is really just 1 over 6. And so in my next step, I can say this is 1 over 6, and then that numerator, 4 times 3 times 2 times 1, that is 4 factorial. And so the Laplace inverse of 4 factorial over s to the 4 plus 1 is t to the 4th. Right, let me check. Yep, it's t to the 4th. Okay, so I get 1/6 t to the 4th. All right, so those aren't so bad. I'm going to go from 0 to 60 in about 1 second, and we're going to look at number 4. So number 4 is not the worst that it gets, but it's pretty bad. So I want to find the Laplace inverse of 3s minus 2 all over s cubed times the quantity of s squared plus 4. So that's a lot right there. There's a lot going on. I need to break this up into pieces so that I can get like the form inside to look right. Right now I have one fraction, but it has 4 factors in the denominator. And so I need to do a partial fraction decomposition on that fraction to see all the possible fractions that could have added together to give me that. And so we must get a partial fraction decomposition, it's PFD, on the fraction. And that is going to be the majority of the work. So we're looking at 3s minus 2 over s cubed times s squared plus 4. So the s cubed I'll deal with first. It's possible that there was an a over s that got added to a bunch of fractions. S cubed, it starts as an s, and then plus there's a bs squared that could have been involved, plus there's a c over s cubed that could have been involved. So the s cubed, what we're seeing there is s. S is a linear factor, but there are three of them, right? That power tells us 3 of them, which is why I have to have these 3 fractions that could have come together to give us that s cubed in the bottom. The s squared plus 4 does not factor at all, and it is quadratic. And because it is quadratic, the numerator has to be linear. So we'll put in a ds plus e. Okay, the next step in a partial fraction decomposition is to multiply everything through by the common denominator of s cubed times s squared plus 4. When I do that, the fraction on the left becomes just 3s minus 2 because the whole fraction clears. And that's equal to a. When I multiply the a over s by the common denominator, I'm left with an as squared times s squared plus 4 because one of the s's divided out with the s on the bottom. Plus b, the b over s squared. The s squared clears out 2 of the s's, so we have bs times s squared plus 4. The c over s cubed, all the s cubes go away, so I'm left with plus c times s squared plus 4. And then the ds plus e over the s squared plus 4, the s squared plus 4's go away. So I have in parentheses ds plus e times the s cubed. Okay, now I have to multiply this all out, and then I have to equate coefficients. So this equating coefficients thing comes up over and over again in this class. All right, I'm going to multiply everything out very carefully first. So 3s minus 2 is equal to as to the fourth plus 4as squared plus bs cubed plus 4bs plus cs squared plus 4c plus ds to the fourth plus es cubed. Now I'm going to go through and highlight things that have like terms. So the s to the fourth terms, I have an as to the fourth plus a ds to the fourth. On the left-hand side, I have 0s to the fourths. So my first equation is a plus d is equal to 0. Then I'm going to go to s cubes. I have a bs cubed and I have an es cubed. So, and I have no s cubes on the left, so my second equation is b plus e is equal to 0. Then I have my s squared terms. I have 4as squared plus cs squared. I have no s squareds on the left, so my third equation is 4a plus c is equal to 0. Then I have my linear term, just one, the 4bs, and I do have a linear term on the left-hand side, so my fourth equation says 4b is equal to 3. And then last is the 4c, that's my constant. So my fifth equation is 4c is equal to minus 2. All right, it looks like I can start solving from the right and work my way to the left. In the fifth equation, 4c equals negative 2, so c is equal to a negative 1/2. In the fourth equation, 4b is equal to 3, so b is equal to 3 over 4. In the fourth equation, I replace the c with a negative 1/2, and 4a minus a half is 0, which means 4a is 1/2 and a is 1/8. In the second equation, I replace the b with 3/4 plus e is 0, so e is a negative 3/4. In the first equation, I replace the a with 1/8, so 1/8 plus d is 0, which means d is negative 1/8. And so what I have here now is a new way to write out my Laplace inverse. So the Laplace inverse of 3s minus 2 over s cubed times s squared plus 4 is equal to Laplace inverse of a over s, so that's 1/8 over s, plus b over s squared, so it's plus 3/4 over s squared, plus c, and c is, we've got a minus, so minus 1/2 over s cubed, plus ds plus e. I'm going to split that up, so I'm going to deal with ds over s squared plus 4. That's going to be a minus sign actually, so minus 1/8 s over s squared plus 4, and then plus e, and e is negative as well, so minus 3/4 over s squared plus 4. Okay, so instead of taking the Laplace of like one fraction, it actually turns out I have to take the Laplace inverse of 5 fractions, and none of them are quite right. So I'm going to start working on that too. First, I'll use linearity to pull all those fractions out and look at each of the individual ones on their own. So this is equal to 1/8 Laplace inverse of 1 over s plus 3/4 Laplace inverse of 1 over s squared minus 1/2 Laplace inverse of 1 over s cubed minus 1/8 Laplace inverse of s over s squared plus 4 minus 3/4 Laplace inverse of 1 over s squared plus 4. Okay, let's see what we have to do. All right, so the 1 over s, Laplace inverse of 1 over s, and I apologize because I do have some of these memorized, so I will use that fact, and eventually you will have some of them memorized as well. Laplace inverse of 1 over s is just 1, so this first term is just 1/8. The Laplace inverse of 1 over s squared, that 2 is 1 plus 1, so this must be a t to the 1. So I get plus 3/4 times t. The 1 over s cubed, the 3 is 2 plus 1, so I am missing a 2 factorial. So I have my minus 1 over 2, but I'm going to divide by a 2 factorial and put in a 2 factorial in the numerator. So now it's in the right form, and in the next line I'll evaluate it. Minus, well, it looks like Laplace inverse of s over s squared plus 4, k is 2. We can already deal with that one, and when it's s over, that is a cosine one. So I get minus 1/8 cosine of 2t. And then the minus 3/4 Laplace inverse of 1 over s squared plus 4. This looks like a sine one. In the bottom, I see k squared is 4, so k is 2, and I need a 2 in the numerator. So on the outside, I have my minus 3 over 4, and I'm going to put in a times 2 in the denominator, have my Laplace inverse, and put a 2 in the numerator over s squared plus 4. Okay, now let's do our final step. This is 1/8 plus 3/4 t minus 1/4 t squared minus 1/8 cosine of 2t, and then minus 3 over 8 sine of 2t. And that's it. That's done. So that was actually a lot of work, having to do a partial fraction decomposition in there, and then having to use linearity to write things out correctly, and then, do some minor algebra tricks, funny looking ones and such. All right. Next topic is transforms of derivatives. Now, if we were to take the Laplace transform of y prime of t, remember I'm using little y here. Before we're using little f, and so the Laplace transform of little f gave us big F. The Laplace transform of little y gives us big Y. Okay? So I've got that written right here. Laplace of little y of t gives us big Y of s. The first derivative, Laplace of y prime of t, gives us s times big Y of s minus little y of 0, where this little y of 0, that came from an initial condition. So we apply Laplace transforms to IVPs. We need initial conditions in order to make this work. The second derivative, if we take the Laplace transform of it, we get s squared big Y of s minus sy of 0 minus y prime of 0. And these are also initial conditions that were given. And so once we've taken the Laplace transform of the differential equation, we're going to have these little y of 0s and little y prime of 0s. We'll replace them with what their values are because we will know them, okay? In general, the nth order derivatives have a pattern. I forgot to type that in. So the Laplace of the nth order derivative of y of t is going to equal s to the n, big Y of s, minus s to the n minus 1, little y of 0, minus s to the n minus 2, y prime of 0, and so on and so forth. So notice the power of s starts at the order of the derivative, right? N. And then it's multiplied by big Y of S. And then we're done with big Y of S. Okay, so then in the next step, we subtract S raised to 1 less than the order of the derivative times the lowest order initial condition. So that would be little y of 0. Then the power of S goes down again, and the order of little y goes up. And that pattern continues on and on. We're not going to deal with anything too high order. You may see a third order, but no more than that. Okay, it becomes way too laborious to work through. We just want to make sure that you know how to work through and use the table of Laplace transforms and apply that to differential equations. So let's see how this works. We're going to use the Laplace transform to solve this initial value problem. Let me keep my forms right there. We have y double prime minus y prime minus 6y equals 0. And we're given little y of 0 is 1, and little y prime of 0 is equal to negative 1. So let's go ahead and do this. We're going to take Laplace of y double prime, and I'm going to use linearity right away, minus the Laplace of y prime minus 6 times the Laplace of y is equal to the Laplace of 0. So just taking the Laplace of both sides of the equation and using the linearity, the Laplace of y double prime gives me s squared big Y of s minus s little y of 0 minus little y prime of 0 minus the Laplace of y prime gives me s big Y of s minus little y of 0 minus 6. The Laplace of little y is big Y of s, and the Laplace of 0 is 0. Think about integrating 0. You just get back 0. Okay, so we've used our definitions there. Now let's replace some of the things. Y of 0 is 1. Y prime of 0 is negative 1. So put it in with parentheses. Again, y of 0 is 1. Okay, so I'm going to go ahead and distribute and replace stuff. So we have s squared big Y of s minus s plus 1. I will warn you that if your s's look like 5s, you might combine them with 1s and get a 6. Be careful. Okay, and then we've got minus s big Y of s and plus 1 when we distribute the minus sign. And then minus 6 big Y of s equals 0. Okay, I have 3 terms that all have a big Y of s in them. I'm going to bring them together, and I will take the other things, the minus s plus 1 and the plus 1, and move them to the other side of the equal sign. So when I get the Y of s's together and factor them out, I have s squared minus s minus 6 all times big Y of s is equal to s minus 2 on the right-hand side. So then I can, my goal is to isolate big Y of s so that I can take the Laplace inverse of it and get little y of t, our solution. So big Y of s is equal to s minus 2 over s squared minus s minus 6. Well, if I want to find little y of t, I'm going to have to take Laplace inverse of this, and this doesn't look like something I can deal with. So the first thing I'm going to do is factor the denominator. It becomes s minus 2 over, looks like this will factor as s minus 3 times s plus 2. Okay, so nothing cancels out. And then I can do a partial fraction decomposition on this. This I would want to equal, I have 2 linear factors in the denominator, so I have a over the first linear factor, s minus 3, plus b over the second linear factor, s plus 2. And so then I can clear the fractions, and I have s minus 2 is a times s plus 2 plus b times s minus 3. And now I'm going to show you a little trick. You may have seen this in Calc 2. You might not have, so pay attention. You can choose values for S so that you would be enabled to solve for A or B. So what I mean by that is you can be very specific about the value of S that you pick and strategic about it. So I'm looking at maybe let S equal 3. Because if I let S equal 3, then the B times S minus 3, that's going to go to 0. And so then I'll have A by itself. So let's see this work. On the left, I have 3 minus 2 equals A times 3 plus 2 plus B times 3 minus 3. So this gives me 1 is 5A. In other words, A is 1/5. That was nice. Okay. Then I'm going to let S equal minus 2. Because if S is minus 2, then the A term will go away. So when I plug in minus 2, I get minus 2 is A times minus 2 plus 2 plus B times minus 2 minus 3. So on the left, I get minus 4. On the right, I get minus 5B. So B is 4 over 5. Okay, that means that little y of t is equal to the Laplace inverse of big Y of S, which can be written as the Laplace inverse, my curly brackets get worse and worse the longer the day goes, Laplace inverse of 1/5 over S minus 3 plus 4/5 over S plus 2. And this is just 1/5 times the Laplace inverse of 1 over S minus 3 plus 4/5 times the Laplace inverse of 1 over S plus 2. So I'm going to go up to our little table that we had. Try not to go too fast to make you dizzy. And it looks like I am interested in C. If I take the Laplace inverse of 1 over S minus A, I get e to the AT. Okay. Note that S plus 2 is S minus a minus 2. And so when we take the Laplace inverse here, we get 1/5 e to the 3t plus 4/5 e to the minus 2t. And that is our little y of t. It is the general solution for our differential equation. Now let's see one more here. I'm not sure why I gave myself so much room, but you might have needed it. All right. There are a couple more of these first and second order IVPs to check out in the book, but I'm going to do one more where we're dealing with y double prime plus 9y equals 0, y of 0 is 1, and y prime of 0 is 0. So I take the Laplace transform of y double prime plus 9 times the Laplace transform of y equals the Laplace transform of 0. The Laplace transform of y double prime is s squared big Y of s minus s little y of 0 minus y prime of 0. Plus 9 in the Laplace of y is just big Y of s, and this is all equal to 0. I'm going to replace y of 0 with 1 and y prime of 0 with 0. Okay. Now I'll gather my y of s terms together and factor it out. So we have s squared plus 9 times big Y of s minus 1 is equal to 0. Isolating big Y of s, I get y of s is 1 over s squared plus 9. I don't have to do much of anything. Oh, you know what? I made a mistake. That minus 1 should have been minus s times 1, which is just s. So I have an s in my numerator. Okay, perfect. Now I can get my general solution. Y of t is the Laplace inverse of big Y of s which is going to be the Laplace inverse of s over s squared plus 3 squared, just so we see it in the right form. This is a sine of 3t. Right? Is s with sine or is s with cosine? No, s is with cosine of 3t. And that right there demonstrates why I give the table of Laplace transforms, because I don't want you to focus necessarily on memorizing them as like a thing you have to do. You may accidentally memorize a few of them, but I don't want somebody sitting in a test unable to come up with what the Laplace inverse of something is because they couldn't remember it, right? The table's there for us. We already have to manipulate things quite a bit in order to make it all work. So you will have the table, right? That is all I have for you. You know, a couple examples, solving some IVPs in here. There's more in the book and there's more in our learning management system. But as always, if you have any questions, please reach out.